welcome again to the new lecture of this course, Properties of Materials. So, let us just briefly recap first what we did in the last class. So, in the last class we first looked at differences between true and engineering strains. So, first thing that we saw that true strain is equivalent in compression and tension, whereas true strain, whereas engineering strain is not, and then true strain is additive. So, if you deform a material in different passes and you calculate the strain from 1 to 2 and 2 to 3 and 3 to 4 and then calculate the net strain, all those pass strains they add up to net, and then the net volume change, if there is no volume change, then epsilon 1 plus epsilon 2 plus epsilon 3 will be equal to 0, whereas this condition will not be obeyed by the engineering strain. Then we looked at the cases of small strain. So, we basically looked at the cases of strain of small magnitudes, and there we basically looked at what is shear strain. And shear strain basically is defined as, so you can say that for a 3D body with various displacements, you can define three shear strain gamma xy as which is equal to gamma yx, this is equal to del u by del y plus del v by del x. Similarly, you can write gamma yz which is equal to gamma zy, this is equal to gamma w del w divided by del y plus del v divided by del z. Similarly, we can write gamma zx which is equal to gamma xz which is equal to del w by del x plus del u by del z. You can write these also as gamma 1 2 or gamma 2 1. These can be written as gamma 2 3 or gamma 3 2. Similarly, here you can write gamma 3 1 or gamma 1 3. So, these are the relations for shear stresses. So, now if you write the overall tensor, the tensor can be written as epsilon 1 2 epsilon 1 1 1 2 epsilon 1 3 epsilon 2 1 epsilon 2 2 epsilon 3 3 epsilon 2 3 and then 3 2 and then 3 3. Now, out of these three are principal strains, and one on the off diagonal terms they are shear strains. So, mathematically speaking, however, so the mathematical strain, or we can say tensorial strain, epsilon ij turns out to be half of engineering shear strain. Okay. So, there is a whole derivation for it, we are not going to go into that, but the relation is epsilon ij is equal to half of gamma ij. So, if you just replace this here, so basically the way you define then epsilon yz is equal to epsilon zy is equal to half of gamma yz, this is equal to half of del v by del z plus del w by del y. Similarly, you can write epsilon zx to be equal to epsilon xz, this will be half of gamma xz and this will be half of del w by del x plus del u by del z. Similarly, we can write gamma epsilon xy which is equal to yx which is equal to epsilon yx which is equal to half of gamma xy, or you can write gamma yx which is equal to half of del u by del y plus del v by del x. So, if you now replace these terms there, so what you basically get is epsilon ij will become equal to epsilon 11, epsilon 22, epsilon 33, these are the diagonal terms. Then we have half of gamma 12, half of gamma 13, here we have half of gamma 21 or 12, let us say. Then we can write half of gamma 23, half of gamma 13 and half of gamma 23. So, this is what the strain tensor is going to look like. Now, what we are going to do is that we are going to do transformation of, we are going to apply the transformation of axis to strains. Okay, we saw the transformation of axis to stress. Now, we will look at the transformation axis to strains. So, now this is applicable only to small strains. We can't apply to large strains because of deformation causing changes. So, the cosines, the L values, they change as the deformation happens on a large scale, because the materials are mostly polycrystalline. So, as a result, that grains deform, they reorient themselves along certain different directions. So, for example, for in the beginning your grain structure may be something like that, and each grain has a different crystalline orientation, and when you deform it, when you extend large deformation, the grains may become like this. So, they may become oriented. So, as a result, the stress and strain tensors will change, because let us say if this was, in this case the UVW was in this direction, this is UVW, this is UVW, this is UVW, and so on and so forth. Like this. It is possible that in the deformed grain structure your UVWs will become something like this. To some extent, maybe not to this extent, this is very exaggerated picture, but what I am trying to convey is that your stress and strain tensor, your stress and strain tensors will change because the angles will change. As a result, so you will have a change in angles. So, as a result, the L values will change, and your stresses and strains with respect to reference axis will also be different. So, as a result, we cannot apply this to large strains, we can only apply it to smaller strains. So, this is something that we have to keep in mind. Now, the relation basically is similar. So, mathematical relation is very similar to basically you can say stress. So, we can say that epsilon ij is equal to Lim into Ljn to epsilon Mn. So, the summation over different values of M and N is implicit. So, it is built in there. Okay. So, summation for M is equal to 1 to 3, N is equal to 1 to 3 is implicit. Okay. So, now let us take first example. Let us take, so you can write epsilon x prime, or let us do it differently. Let us try to do it in the, or we can write epsilon 1 prime, 1 prime. So, let us take the case of epsilon 1 prime, 1 prime. So, if you look at the relation, we said that epsilon ij is equal to LIM LJN epsilon MN. Okay. So, I and J values are fixed, alright. So, this becomes basically, so essentially we are going to sum over L of 1 prime m, L of 1 prime n to epsilon mn. This is what the sum is going to be. So, if we now write it, so this will be L 1 prime 1, L 1 prime 1 epsilon 1 1. Second term, so the m remains constant in the row. So, let us say it is 1 prime 1, 1 prime 2, n changes from 1 to 2 and this becomes epsilon 1 2. Similarly, we can write this as L 1 prime 1, L 1 prime 3 epsilon 1 3. The next one will be L 1 prime 2, L 1 prime 1 epsilon 2 1 plus L 1 prime 2, L 1 prime 2 epsilon 2 2 plus L 1 prime 2, L 1 prime 3 epsilon 2 3, and this will be epsilon 1 prime 3 epsilon L 1 prime 3 L 1 prime 1 epsilon 3 1. This will be L 1 prime 3 L 1 prime 2 epsilon 2 3 2, and this will be L 1 prime 3 L 1 prime 3 epsilon 3 3. Okay. So, we can now simplify this. So, we can make epsilon 1 1 is equal to epsilon 1, epsilon 2 2 as epsilon 2, epsilon 3 3 as epsilon 3, and we convert these epsilon ij is equal to epsilon ji, and epsilon ij is also equal to epsilon of gamma of half of gamma ij. So, if we make these replacements, what we get here is epsilon 1 prime is equal to L 1 prime 1 square epsilon 1 square plus L 1 prime 2 square epsilon 2 square plus L 1 prime 3 square epsilon 3 square plus L 1 prime L 1 prime 2 into L 1 prime 3 to gamma of 2 3 plus L 1 prime 3 L 1 prime 1 gamma of 3 1 plus L 1 prime 1 into L 1 prime 2 gamma 1 2. So, this will be the expression. So, you can see that 2's are missing here because we have replaced epsilon with gamma. So, as a result there is a factor of half. So, 2 and 2 they cancel each other in all the terms. So, as a result it becomes equal to 1. Alright. So, this is the expression that we get for epsilon 1. Similarly, you can do things for epsilon 2 2 prime and epsilon 3 3 prime. All the principal strains can be calculated in a similar manner. Now, let us say similarly if I want to do epsilon I, if I want to work out epsilon ij, okay, let us say, so it could be epsilon x prime y prime, or let us say we do epsilon 1 prime 2 prime. So, if I do epsilon 1 prime 2 prime, again follow the same formula, that is epsilon ij will become LIM LIN epsilon mn. So, essentially it becomes L 1 prime m L 2 prime n epsilon mn, and this is what is going to be summed over. So, when you do this now, it becomes L 1 prime 1 L 2 prime 1 epsilon 1 1 plus L 1 prime 1 L 2 prime 2 epsilon 1 2 plus L 1 prime 1 L 2 prime 3 epsilon 13 plus L1 prime 2 L2 prime 1 epsilon 2 1 plus L1 prime 2 L2 prime 2 epsilon 2 2 plus L1 prime 2 L2 prime 3 epsilon 2 3 plus L1 prime 3 L2 prime 1 epsilon 3 1 plus L1 prime 3 L2 prime 2 epsilon 2 3 2 plus L1 prime 3 L2 prime 3 epsilon 3 3. This will be the full expansion. So, if you now again modify by making epsilon ij is equal to epsilon ji and epsilon ij is equal to half of gamma ij, and then we can modify this as, so we can write this in terms of gamma 1 prime 2 prime. This will become equal to 2 into L1 prime 1 L2 prime 1 epsilon 1 plus L1 prime 2 L2 prime 2 epsilon 2 plus L1 prime 3 L2 prime 3 as epsilon 3, and then we will have the terms related to gamma 1 2 gamma 2 3 and gamma 3 1. So this will be L1 prime 1 L2 prime 2 plus L1 prime 2 L2 prime 1 into gamma 1 2 plus L1 prime 2 L2 prime 3 plus L1 prime 3 into L2 prime 2 epsilon gamma 2 3 and plus we can make it L1 prime 1 L2 prime 3 plus L1 prime 3 L2 prime 1 into epsilon 3 2 sorry epsilon 1 3. What have we taken? Just one second. 1 prime 2 2 prime 3 1 prime 3 2 prime 2, this is epsilon 2 gamma 2 3 and this will be gamma 3 1 or 1 3. So, this will be the full expansion for gamma 1 prime 2. So, as a homework, try expressions for epsilon 2 and epsilon 3. Similarly, you should try the expressions for, let us say, 1 prime 3, 2 prime 3 prime and so on and so forth. Okay. So this will help you practice on how to write these transforms. So, this is what is about the transformation of strains. You can do a simple problem on this. So, I will not do it in here, but a simple problem is to verify whether it works at small. So, simple problem can deal with large versus small strains. So, this could be, let us say you take a block of dimension, let us say A by A in X and Y. So, this deforms, let us say, to a very small change. So, this could be dx and this could be dy. Okay. So, let us say this becomes from A to, I do not know, 1.02 A and this whole thing, and this thing becomes, sorry, .98 A. So you can work out, so the thing that you have to do is that work out. So you can just look at the diagonal, let us say in this case, and diagonal in the next case. So work out diagonal lengths, calculate strain using diagonal, and then calculate strain using. So let us say this is the reference axis. So the axis will, so this is x y, this will be your x prime. So assuming that the angle is close to 90 degrees, you can work out the strains as it will be epsilon. So you can say epsilon 1 prime will be equal to L 1 prime 1 epsilon 1 into L 1 prime 2 square epsilon 2. So this will be the x strain, this will be the y strain, and you can see whether the values match or not, and you will see the values will match. Okay. So when you calculate, so there will be a match, all right. When you do the same thing for a large deformation, so for a large deformation situation is like this. So you have x, y, you have this block. So this was A and A, this block changes to something else. So here we have a change which is, let us say this is 1.5 A and this is 0.67 A, assuming that the volume remains the constant. So this is how you have to choose. So again look at the diagonal. Okay. So calculate. So instead of, what you can do is that instead of using true strain, you can use engineering strain. Use engineering strain for simplicity, or if you want to use, or even true strain. So both of them should give you that at least a rough idea. Okay. So calculate the diagonal related strain, and again calculate the strain from transformation of axis. So this will become x prime, but here you can see the angles are not no longer 45 degrees. So as a result, in this case it is 45 degree, but in this case it is not equal to 45 degrees. So you will have to work out the angles clearly, and you will see the strains will not match. So this will be sort of homework for you. So what you have to do is that you take this block, carry out a small amount of deformation where the strain is very small, calculate the strain. So what you have to do is that basically you carry out a small deformation with very small strain, calculate the strain using diagonal, and then calculate the strain using transformation of axis, and you will see both the strains will nearly match. But if you carry out a large deformation, again you apply the same procedure, you will see that the strains will not match, and this will sort of give you an idea of why is it applicable at smaller strain and why is it not applicable. So let us now, we are nearly at the end of the lecture, so let us summarize this lecture. So what we have done is basically we have looked at the transformation of axis for strain. We also looked at the relation between epsilon ij and gamma ij. So we saw that epsilon ij is equal to half of gamma ij for mathematical reasons. So this is basically shear strain, which is the engineering shear strain. So essentially you calculate using this tan theta, right? This is theta. So this is delta deformation, and this is the original length, let us say L naught. So, tan theta will be equal to delta divided by L naught. For very small angles, this can be for small theta, I can write this as theta, which is equal to delta divided by L naught, and basically it was the shear strain. So, del gamma ij was equal to, let us say for example 1 2 was equal to gamma, so del u by del y plus del v by del x, alright. So, this was the shear strain, whereas this is the overall strain that you get for, so this combines basically both translations in both the directions. So, this is for mathematical, so this is your mathematical strain, you can say, and it can be proved that this mathematical strain is equal to half of gamma ij. We do not have time to go through the derivation here, but if you look into any books on mechanics, you can easily find about it. And then I have given you a problem on how to examine the differences at small and large deformations. So, this is something you have to do as a homework. So, we will stop here today. In the next lecture, we have done the discussion on basically the tensorial stress, the tensor form of stresses, the tensor form of strains, the transformation of axis in both cases. What we have not done is the Mohs circle thing, but if we get time later on, we will do it. But that's something you can read from the books, and so using this information, you can get into the mechanics of deformation if you know the tensorial way of working with stress and strain. So, now what we will start is we will basically move into elastic theory of elasticity for various materials. Thank you very much.